Welcome to my video course on railway safety and systems engineering, where today we will unpack the fascinating world of safety integrity levels, or SIL. If you've ever looked at a massive, complex rail network and wondered how on earth engineers guarantee that trains won't collide, even when computer systems inevitably glitch, well, you are in exactly the right place. In this explainer, we're going to break down the highly structured methodology that makes modern automated transit possible. Okay. Let's take a quick look at our roadmap. We'll start with the software problem, move into SIL concepts, define SIL 1 through 4, look at some real-world railway examples, and finally discuss balancing safety and complexity.
Section 1. The software problem, a new challenge.
To really appreciate our framework today, we first need to understand the unique engineering problem that popped up with modern processor-based systems. You see, before computers, safety was largely mechanical or electrical, but software introduced a completely new variable. Think about it. You can physically test a steel weld, right? You can X-ray it, stress test it, and definitively say, yes, this is structurally sound. But you simply cannot test every possible input, output, and combination of states in a complex software program. And because you can't test every single outcome, you introduce the risk of systematic failures. Basically, bugs hidden deep in the code, just waiting for the exact wrong circumstances to activate. So, since we can't fully test the final software product, our safety assurance has to fundamentally shift. We literally have to shift our trust from the end product to the engineering process itself. The logic is, if the process is flawless, the product should be too. This demands incredibly strict production processes, the absolute highest competence of engineers, massive amounts of rigorous documentation for traceability, and, this is absolutely crucial, a strict independence of roles. The person who writes the code can never, ever be the same person who tests it. Let's move on to Section 2, SIL concepts, measuring integrity. So how does this intense focus on process build into a structured solution? Well, that brings us to SIL. A safety integrity level essentially defines the degree of confidence we need that a system will perform safely. It's basically a measure of reliability for safety-critical tasks. And crucially, it inherently includes the system's ability to revert to a safe state if a failure does occur. Like, if the power completely cuts out, the system must naturally fail into a state that keeps everyone safe. For example, automatically turning all track signals to red. But here's the major paradox engineers face. How do you measure something you can't even see? Since we can't assign an exact numerical probability to a hidden software bug, we rely on a foundational logic instead. We accept that applying more rigorous design, verification, and validation methods naturally results in a lower probability of failure. Put simply, the better and stricter the methodology, the higher the integrity. All right, Section 3, defining SIL 1 to 4, scaling integrity. This brings us to the actual scale used by engineers worldwide. The SIL scale steps up from 0 to 4. SIL 0 represents basic integrity for non-safety functions. These are things where a failure might be super annoying, but nobody gets hurt. From there, it scales up through SIL 1, 2, and 3, all the way to SIL 4. SIL 4 represents the absolute highest possible integrity, requiring the most rigorous, expensive, and time-consuming engineering methodology available. Achieving these higher levels, like a SIL 3 or SIL 4, demands escalating engineering principles. You can't just code a SIL 4 system in your basement on a weekend. No way. It requires top-down design methods, strict modularity so faults don't cascade, verified component libraries, and rigorous verification at every single phase of the lifecycle. Literally, every single decision must be highly auditable and independently assessed. Let's jump into Section 4, Railway Examples, SIL in Action. Let's ground all this theory in reality by looking at a physical rail network. The perfect example of SIL 4 in action is the interlocking system. You can think of the interlocking as the brain on the tracks, because it directly controls physical objects like the points that switch trains between tracks and the signals that tell drivers to stop or go. It acts as the ultimate safety layer against collisions. If a human operator accidentally asks to route two trains onto the exact same track, the SIL 4 interlocking logic will flatly refuse to execute that command. Conversely, not everything needs to be SIL 4. Operator interfaces, the control panels, and the dispatch desks usually only require SIL 0 to SIL 2. Now you might be wondering, why? Well, because even if a computer display completely fails, or a human operator makes a terrible error and requests a dangerous route, that SIL 4 interlocking layer down on the tracks will step in to prevent an unsafe movement. The interlocking is the ultimate failsafe. Sure, An operator relies on accurate data to keep trains running efficiently, but the actual communications links feeding their screens do not have to be SIL 4. The railway will still be completely safe if those screens go blank. I mean, it will cause major delays for sure, but it won't cause a crash because that local trackside interlocking guarantees the fundamental safety. And finally, Section 5. Safety versus complexity, the engineering balance. At this point, you might be asking a very logical question. If SIL 4 is the safest, why don't we just make absolutely everything? The screens, the communication networks, the dispatch phones, the desks, SIL 4 as well. Wouldn't that give us the ultimate perfect railway? The answer is a harsh lesson in engineering practicality. Designing systems to meet SIL 4 is incredibly complex, extremely time-consuming, and massively expensive. But more importantly, enforcing that level of rigorous fail-safe architecture everywhere can actually result in a system that breaks down more often. Highly sensitive SIL 4 systems are designed to shut down safely at the very first sign of any anomaly. So, if everything is SIL 4, your railway will constantly be shutting down, which completely tanks your overall operational reliability. Furthermore, we have to remember that fail-safe does not mean 100% safe. When a highly sensitive SIL 4 system safely shuts down trains due to a minor equipment fault, the signalers and operators are forced to use manual, degraded mode procedures to get trains moving again. And the second you revert to manual procedures, you bypass your computer safety nets and introduce the massive risk of human error right back into the equation. A system that cries wolf and shuts down too often actually becomes less safe overall because of the human interventions required to fix it. So, as you reflect on this delicate balance between safety, complexity, and reliability in modern system architecture, think about how you might approach this challenge in your own engineering designs. How do you protect against a total catastrophe without designing a system so sensitive that it paralyzes the very operation it was built to manage? It really is the ultimate puzzle for systems engineers. Thanks, we can see in next video.